Okay, now C circuit. Okay. That's an LC circuit. What's the purpose of that battery? To charge up the capacitor. Okay, right? You close switch 1, and the battery can charge the capacitor until you can't put in, until it can't push any more charge on the plates. The capacitor is saturated. Then you open S1. What do you have? A fully charged capacitor, right? Now, if you close S2, what's going to happen? Well, that's what this section is about. What's going to happen is pretty cool. Okay. First of all, before you close, okay, so you open S1 and you're about to close S2. Where's all the energy in the circuit? Disregard the battery. In the electric field between the plates and the capacitor, right? Okay. If you close S2, what can happen? What does that allow? Positives want to get the negatives, don't they? Okay. So it's going to be a current flow from the positive plate through the inductor to the negative plate, right? Will it be a constant current flow? It'll be time variable. So there's going to be a DIDT, a non-zero DIDT. So there's going to be a voltage across the inductor as the current sloshes through from the plates of the capacitor through the inductor. Okay? So basically what's going to happen is you're going to have a situation where you've got all of the energy here, okay, and then current begins to flow, okay, and they recombine until eventually you have a negative charge here. You know, maybe you start with a positive charge here, negative charge here. Eventually, halfway through the cycle, you'll have all negative here, all positive here. Then it'll slosh back. It'll just go back and forth, and the current will flow half of the cycle in a clockwise direction, half of the cycle in a counterclockwise direction, in a sinusoid. And if you don't believe me, then we'll believe Ohm's law. I'm sorry, not Ohm's law, about the Kirchhoff law. They're both right. All again, Kirchhoff. So if you start here and you go around that pocket, what are we going to have? We've got U over C. That's the voltage across the capacitor, right? And then minus L DIDT. And that equals 0. So let's do this. Negative Q over C is equal to L DID. Okay, well, remember I is equal to this can be written as L second derivative of Q with respect to time. Yes? Make sense? Now I'm going to divide through by L, so I'll have negative 1 over LC times Q is equal to second derivative of Q dt. So that's a second order differential equation. Right? Now, you tell me, you smart people, Q is a function of time. Okay? Can you tell me the function of time that you can take the derivative of once, then take the derivative again, and end up with the same function with some negative constant on it? What kind of function allows it? E. E might do it. Anything else? What kind of function? What kind of function behaves this way, that you can take the derivative of it 2 times, get the same function back from just a constant, negative constant front. What is it? Cosine or sine? I think either one of them, right? It's a sinusoid. A sinusoid. You never heard of sinusoid? It's like something that needs to get removed from your nasal passage. So, let's see if that's true. If Q is a sinusoid, Q function of time kind of equal to some Q0, some initial charge, times, let's use cosine. Cosine of omega t. Okay? Now, if we take the time derivative of this, Q dot is going to be equal to, if you take the derivative of cosine, you get negative sign, right? Negative Q0, I have to bring the derivative of whatever's on front, so it's omega sine of omega t. And then take the derivative again, double that. And you take the derivative of sine, you get positive cosine, right? So it's going to be negative Q0 omega squared cosine of omega t. But remember, the original was Q0 cos, so we've got Q0 cos in there, so we can write that as negative omega squared Q. So Q double dot is equal to negative omega squared Q. Yeah, a cosine function works, right? Okay. So, and notice that we've got a negative constant out front. Remember, omega is the radial frequency of the function. It's how fast it changes in time, right? So 1 over LC must be omega. So omega is equal to 1 over LC square root. So that has something to do with how fast the circuit oscillates. And I don't know if you know this or not, but omega is equal to 2 pi divided by the period. The amount of time it takes to do 1 whole cycle. So the period of this circuit, T, will be equal to 2 pi divided by the square root of LC. Now, basically what you've got, well, so this is the way the charge changes with time on the plate of the capacitor, on one of the plates of the capacitor, right? So at time equals 0, you've got cosine 0, which is 1. So that's the initial charge, whatever initial charge has been put on the capacitor, that's what you got at time equals 0, right? Okay. And it goes as a cosine function. Could we find the current flow through the circuit? How would we do that? Yeah. Looks like we already found it. It's right there. Okay, so I, the current through the circuit, I is equal to negative Q0, and omega is equal to 1 over the square root, so it's square root of LC times the sine of 1 over the square root of LC. That makes sense? That's the current in the circuit. Can you find the voltage across the inductor? What do you have to do? Take the derivative again, dIdt. So that's this right here. So the voltage across the inductor is going to be equal to negative Q0 over LC times the cosine of T over the square root of LC. Oh, but then just multiply by L, so this L goes away. There's 0 over C. So that's the voltage across the inductor. What about the voltage across the capacitor? Can you find that? Yeah, the voltage across the capacitor is just going to be Q over C, right? So it's going to be okay, notice no negatives. What is the negative of the other? It has to be because you can add them up around the circle. Or they won't be. So if you were to graph this, these would be mirror images of each other as time progresses. This would be a negative going cosine, this would be a positive going cosine. By the way, these circuits, LC circuits, are super important in any kind of transmission or reception. Right? There's a carrier frequency. Like, what's the carrier frequency of a local radio station? When you know that. There's a talk radio station on 96.5. Okay. What is that? That's 96.5 megahertz. Million cycles per second. Okay. There's a circuit like this, an LC circuit in the transmission station. Okay. And the carrier frequency oscillates 96,500,000 times every second in forth like a cosine. Okay. That sends the electrons that are free to move in the middle of the tower up and down, up and down, and up. Okay. When you do that, guess what? Okay. The electric field lines basically oscillate up and down just the way the electrons do. Right? They're changing in time, that creates a changing magnetic field, perpendicular. A changing magnetic field, according to Faraday's law, creates diameter, and that's different. So to pi e squared over 4. What was the diameter? They give the diameter. Okay, so pi times 0.15 meters squared over 4. Does somebody mind calculating that?
1.5
Oh, okay. Okay. So that's, that would be 1.5 times 10 to the minus third. And that's how it's squared. Would somebody do this one? 2.25 times 10 to the minus 6 square meters, all divided by 4. What is 2.25 pi divided by 4? Very odd. 1.8 times 10 to the minus 6 square meters. Okay, so we have the area. What was the number of terms again? What was it, 50 terms? Okay, so this is going to be 4 pi times 10 to the minus 7 Teslas meters per minute. We'll multiply that by A, which we just calculated, would be 1.8 times 10 to the minus 6 meters squared. Okay, we found N was 50, so 2 times that would, I'm sorry, 50 squared would be 2.5 times 10 to the third. No units there. And it's 5 centimeters long, so that's 1/20th of a meter. So what units do we end up with? The meters cancel here. You've got Teslas times meters squared, that's a Weber. A Weber per amp is a Henry. The unit for inductance is the Henry.
I do not
I don't believe you got this proved. Okay, so yeah, so the units are good. What do we have? 10 to the third times 10 to the minus 6 is 10 to the minus third times 10 to the minus 7 is 10 to the minus 10. So that times 10 to the minus 10 Henry squared. And 2.5 times 4 is 10. 10 times 20 is 200. 200 times 1.8 is 360. What is 360 pi? 360 pi.
1130.9.
1131. So that's going to be 1.13 times 10 to the minus 7 for 113 nanoamps. So that should be the inductance. Connect each, okay, so a metallic laboratory spring is, if you connect such a spring in an electric circuit, how much self-inductance must you include? Okay, so there's the self-inductance. So just to show you the use of that equation, and shame on me for not then 4 to the next. Did you look it up?
Not yet, not yet.
Um, one inlet, one standard inlet. Turns of wire and carries a current of 80 amp, calculating A, the magnetic field in the solenoid, B, the energy density in the magnetic field in the coil is filled with air, and C, the total energy contained in the coiled magnetic field, assuming the field is uniform, and the inductance of the solenoid. Okay, so there's a lot there, and that's not a bad question. Okay, because we've dealt a lot with figuring out the magnetic field of the coil, and now we talked about the inductance of the coil. So let's see. It's 25 centimeters long, so L is equal to 1/4 meter. The magnetic field of the solenoid is N u sub 0 I, right? How many turns were there? How many? 400? Okay, so you can also write this as capital N u sub 0 I divided by L, right? Because little it is big N over L. Okay, so let's go ahead and plug into this. That's 400, so it's 4 times 10 to the 2 times u sub 0, which is 4 pi, times 10 to the minus 7 Teslas meters per minute, times, what was the first? 80 amps. And then we divide that by the length of 1/4 meter. Okay, let's check the units first. These amps cancel, these meters cancel, you're left with Teslas, that's right. Okay, so this 4 comes up top, 16 times, so 4 times 4 is 16 times 4 is 64 times 8. 4 times, what's 4 times? So it's 64. That would be 256. And that would be 4 times 64. 8 times 64 would be 512. So this would be 512 pi times 10 to the negative 4. Is that right? Okay, so that would be
161.
point, what is it, 5.12? No, I'm sorry. So what is 512 pi?
0.161.
So the total is 1.1. Okay, so, no. That's good. Okay. So there's the magnetic field of the solar. So 0.161 Tesla. So that's the magnetic field inside the region, enclosed by the sun. Is that the magnetic field? Part B, the energy density in the magnetic field for the solenoid is filled with air. Okay, well the energy density, I think I just erased that equation, but it's only U to B is equal to D squared divided by 2 U sub 0. So we just found B, so take that value and square it, so it's going to be 1.61 times 10 to the minus 2 times 10 to the minus 1. Tesla squared divided by 2 times u sub 0, so it's going to be 8 pi anybody mind running through that and telling me like, oops, this whole thing is squared? Right? That top number is squared. Units do work, you do get joules per cubic meter. Has somebody done this calculation? 0.161 squared divided by 8 pi times 10 to the minus 7.
10,313.
Use of V is equal to 10,000 what?
313.6.
313 joules per cubic meter. Anybody else get that? So that's part A, part B. Part C is the energy density equation. The energy stored in the magnetic field. Okay, here I just found the energy density in the magnetic field. So I found part D. Part C is the energy stored. Okay, the energy stored, big use of V is equal to, what is that, 1/2 L I squared? Isn't that right?
Yeah.
Is that the energy stored? Or is that the power?
No, yeah, it's
Okay, so, L, have we found L yet? No, we haven't. Okay, L is equal to use of 0 A, then square root of L. Okay, so we need to go ahead and calculate that. 4 pi times 10 to the minus 7 pascals meters per hand. All that multiplied by the cross-sectional area. Okay, give us the cross-sectional area.
Yeah, 0.5 centimeters squared.
Again?
0.5 centimeters squared.
Okay, so that's going to be 0.5 times 10 to the minus 4, or 5 times 10 to the minus 5th meters squared. That's the area. The number of turns was 400, so if you square that, you're going to get 16 times 10 to the 4th, or 1.6 times 10 to the 5th. And you divide that by length, which is 1/4 of a meter. Now that one, 10 to the minus, 10 to the positive, 10 to the minus 5 is 1, 1.6 times 5 is 8. 4 times that top, 8 times 4 is 32, times 4 is 128. So somebody, what is 128 pi? What is 128 pi?
402.
402. So that's going to be 4.02 times 10 to the minus 5th. And units should be other units. Units per meter. Webers per amp, which is that amp? So this is 40.2 microamps. And that's the inductance. So now we've got the inductance. We can come over here. 1/2 times 40.2 microhenries times it was 80 amps. So you square 80, you get 6,400, so 6.4 times 10 to the third. And Henry is a Weber per amp, so that's a Weber turns an amp. A Weber is a Tesla meter squared, and a Tesla is a meter per amp meter. Meters left behind, so that's the meter. So it's about an 8 joule of energy stored in that conductor. Is there more? Yeah, we do it all. Okay, so that's it. That's not a bad problem because it makes you do just about everything that you can do. Find everything that you can find about an inductor. Okay, horizontal. Good. So that's from that section. Take it. Yeah, let's do it in RL circuit. An RL circuit, an LC circuit, and hopefully no, just that. That's it. So, problems 23 through 30, those are all RL circuits. Pick one of those. Which is 80 amps and be squared. 25. Okay, take a look at 25. You've got a 35 volt battery with negligible internal resistance, a 50 ohm resistor, and a 1.25 millihenry inductor with negligible resistance, and they're all connected in series in an open switch with an open switch. The switch is suddenly closed. Hey, how long after closing the switch will the current through the inductor reach 1/2 of its maximum value? Okay. So take a look at this equation over here. Here's the current in that circuit as a function of time. Okay. What they say the voltage was? 35 volts. What they say the resistance was? So 35 over 50, that's going to be 0.7. So the current as a function of time will be equal to 0.7 amps, a volt over an ohm, and times quantity 1 minus E raised to the, okay, R was, what was the R? 50 and L, the inductance. 0.25 milli, 1.25. So what is 50 divided by 1.25?
40.
40. So that's 40 over 10 to the minus third, so that's 40 times 10 to the third. And the units are open for seconds. Okay, so this is the equation specifically for this particular problem. Now, they want to find the time when the current is 1/2 of its maximum value. Can you tell me by looking at this equation what the maximum value of the current is? 0.7 amps. Right. Okay. And when does that occur? At what point in time? Yeah, a long time after that switch is closed, the current will reach its maximum value, which will be 0.7 amps, right? And we want to find out how long after the switch is closed that the current is equal to 0.35 amps. So you plug in 0.35 amps there, and if you do that, then divide through by 0.7 amps, and you'll, so I'm going to take this equation, divide through by 0.7 amps. Okay, now we'll get rid of this, and we'll just have 1/2 equal to 1 minus E raised to the -4 times 10 to the They wanted to find the time when the current is equal to 1/2 of 0.7. So that would be 35, right? Anyway, now I'm gonna add this e to both sides and subtract 1/2. So 1 minus 1/2 is 1/2. So e is e to the negative 4 times 10 to the 4th per second. E is equal to 1/2. I don't like the negative sign, so I'm going to take the reciprocal of both sides. So I'll flip this. This side becomes 2, this side becomes e raised to the positive. So e raised to the positive 4 times 10 to the 4th t per second is equal to 2. Now convert to exponent form, and we just did 4 times 10 to the 4th t per second is equal to natural log of 2. So I'm going to multiply by seconds, divide by 4 times 10 to the 4th. I'll have 0.693 seconds divided by 4 times 10 to the 4th is the time. Natural log of 2 is about 0.693.
That's 4.73 times 10 to the negative
4.73,
5.
1.73, so 17.3 microseconds. So 17 1/3 microseconds after that switch is closed, the current will reach after the time value. Was there more to that one?
The same thing for the unit.
17.3.
How long after the switch is closed is the energy equal to? Okay. Yeah, to do that, where's the energy equation? Right here. There's the energy equation. And now we have to plug in that time, the time-dependent value for I over here. So that has to be squared. So this has to be squared. So 0.7 squared, what is 0.7 squared? 0.49? So yeah. Okay. So let's see. U D is 1/2 Li squared. So what we need to do is take this value. What was L again? What was the effectiveness? 1.25. So that's 5/4. 1.25 micro. 1.25 milli. So 5/4 milli. So that's going to be 5/8 milli. The 0.625 milli. So 6.25 times 10 minus 7. So this is 6.25 times 10 to the minus 7. That's 1/2 times L. And that's Henry's times amp squared is energy joules. Oh, do me this. 0.7 squared is 0.49. So what is 0.49 times 6.25?
3.06.
3.06, and that's gonna be joules. And, this is times 1 minus e raised to the negative 4 times 10 to the 4th per second. And that's gonna be squared. So this is used to be as a function of time for this particular problem. Now we want that to be equal to 1/2 of its maximum. What does it have its maximum value? Time equals infinity, right? Long time after the switch is put. So, and that maximum value will be 0.3 microliters, right? Okay, so take that, divide by all of this, right? You're going to have 1/2 there. You have 1/2 is equal to 1 minus e raised to the negative 4 times 10 to the 4 seconds e, and that's squared. So I don't like the square. So I want to, how do you undo a square? What do you do? A square root. Yeah, so I'm going to take a square root of both sides. I'll take the square root of both sides of this. That goes away. Now I'm going to add this term to both sides, subtract this term. So I'll have e to the negative 4 times 10 to the 4th per second. E is equal to 1 minus 1 over the square root of 2. Now I'm going to convert to exponent form. And I'll have negative 4 times 10 to the 4th per second. E is equal to the natural log of 1 minus 1 over the square root of 2. Multiply by seconds, divide through by negative 4 times 10 to the 4th, and I'll have the time. Negative 1 second times whatever the natural log of 1 minus 1 over the square root of 2 might have to be. Divide that by 4 times 10 to the 4th. That'll be the time when the energy is 1/2 of this. Somebody do that. So you this natural log of 1 minus 1 over the square root of 2
3.069 times 10 to the negative 5. That's what I got.
3.069
Times 10 to the negative 5.
So 3.07 times
or let's do it in terms of micro. 30.6 micro. Is that right? 30.7 microseconds. Okay. So it will take only 17.3 microseconds for the voltage for the current to reach half of its max value. So it will take 30.7 microseconds for the energy stored to reach half of its max value. Yep. Good. Have we done an LC circuit yet? Let's save that. Okay. Okay. Y'all, you were better.
Hold on. And I said I didn't believe
Except for,
Oh.
well, almost everybody.
Listen to that question you said.
What's that?
Listen to what you said.
Quizzes are due